All right, good morning. Test audio. Looks like my audio's okay. Good morning. It is April 26th. It is Monday. Good morning. It is CS-030, working on chapter 17. It is CS-030, inception mode. 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 17. Ah. All right, let's run through our checklist. Good morning, Monty, Josh, Morgan, Ben, Matthew, Faith, Ethan, Carson, and Landon on the inside track there. Ethan, Trent, Sam, Adeline, Thomas, and Dee Dee and Taylor up there in the middle inside track. Great. All right, quick rundown of our, I'm double broadcasting, single broadcast on YouTube. Quick rundown of our checklist. Make sure that you've got your VPN going. Make sure you're in a quiet location and the coffee grinder has been moved to another room. Turn off notifications on your phone or computer. I need to do that. Check. And then on my phone. Check. All right, put on headphones so that you don't get echo if you speak. Shut down any extra apps or browser tabs. Got a lot of that going on my computer. Let's see what else I can shut down. That's it. Open Canvas so you know where we're at. We'll have an assignment, follow-up assignment today after today's content. Make sure you got Eclipse open and connected to Saros. Some of you are there, and we're starting to share through that resource. That's good. Firestorm open and rebake your avatar. Do avatar health, update rebake. And under world and environment, set it to midday, good to go. Set your draw distance to a low number. Go to the classroom. Make sure you can see your classmates' names. Check in at the attendance window. Looks like we're doing pretty good there. And is Dodger laying down? That's the only other thing I got. I think so. I don't hear him barking. Oh, you know what? Dodger's not out. Okay, we'll leave him away today. Digital Dodger. All right, let's bring up a Canvas window so we just see where we're at. Waiting for that to arrive. Okay. So it's Monday, April 26th. Last week of classes. Can you all believe it? We've got today and we've got Wednesday, and then we have our final exam. Tonight, you have your last programming assignment due, the third drone challenge. Gonna have some office hours with some of you this afternoon. And then we'll also have a follow-up quick assessment after today's lecture as well. Our exam will be next week. It should be in the normal slot. I haven't double checked it, but the normal slot for us should be on the calendar. Let's see what we got. I show it as being 8 a.m. on Tuesday. Does that look right? I've got it on 2 slots. Why do I have 2 slots? I'm not exactly sure why I've got it down in 2 slots, but let's iron that out right now. And so I'm going to do that by switching to the dashboard. Final exam policy, we're on Monday, Wednesday, Friday at 9:10 class. Down at the bottom of Canvas, we have our assignments for our exams. There they are. And so Monday, Wednesday, Friday at 9:10. I show Tuesday at 8 to 10 a.m. 8 to 10 a.m. All right, so something here does not reflect that. Let me see if I can make sure that that reflects that. Tuesday, May 5th, 8 to 10 a.m. 8 to 10 a.m. And this one, this is the actual exam. 8 to 10 a.m. No, it's fine. Just says, oh, it's due at 10. That's what's going on. Okay. Available May 8th. Great. All right. I'm sorry, I misread that. When I looked at the calendar there, I thought it said that we had one at 8 and one at 10, but what you see reflected there is a placeholder, which is the placeholder for the exam. Monday, May 4th, it starts at 8 a.m. and it's due at 10 a.m. That's what's going on there. All right, good. I'm glad I cleared that up. Any questions about our final? Okay. If you do, throw them up in chat, and I'll take a look at them when I get a chance. And that's our calendar. Okay. Yeah, Landon, you were a step ahead of me. I'm moving slow. What sections will be covered in the final? All the things that we've covered in the class. And so the way to figure out what chapters they are is to go into Canvas and look at the different modules that are present. So it's working backwards. It's 17, 14, 13, 18, 16, and then Java Collections Framework, which was chapter 15, and then arrays and through the beginning. So the first half of the class, we did things chronologically according to the book, but the second half of the class, I think it makes a little bit more sense intellectually to do a slightly different pattern. But the stuff that's in Canvas is what you should be going off of. And it will include the stuff that we didn't have programming assignments on. So make sure you've reviewed like 13, 14, 17. There'll be a practice exam for some of the multiple choice questions. Yeah. Let me jot down a note to make sure that goes live. Okay. How many coding problems will there be? I'm thinking there are probably going to be 3. If it's not 3, one of those will be broken down into some smaller problems that won't be like full-fledged coding problems. So some of them are like, I mean, the whole class is about coding in some way, or the whole exam is about coding in some way. So you could say all of it is coding problems. But where you're actually writing software, I'm thinking something on the order of 3. I haven't nailed it down yet. Okay, great. So we were talking about search trees. Let me bring up some content. And this is in the context of binary trees. And so while I'm getting that rolling, what I'm going to do here is I'm going to try and bring in some more people into our Saros session. So this isn't showing on screen, but I'm going to go ahead and invite folks that are online. So Ethan Banez, Faith, Frank, Josh. Let me let that pause for a second. Oh, I guess I'm going to leave it off my broadcast screen so that I can have a little bit more screen real estate, which I have on my second screen. Okay. Add Landon. Matthew. Dee Dee. Morgan. Sam. Trent. Thomas. Then go through and adjust some of those to read only. Setting up some read onlys. Setting up some read onlys. Looks like a few of you all dropped out again. I'll do one more pass of invites. All right, that's still settling out. So while that's settling out, let me move forward on our content. All right, so what we've been looking at in this chapter is the idea of a tree. And a tree is a data structure that's like a linked list, but instead of having just a chain of nodes together, instead we can have multiple nodes that split and create a kind of tree structure. If you squint and you look sideways, it looks like a tree. But it has this branching property, and we use the language of trees. We use branch and root, and we use some of the language of family trees in order to talk about it. And what's interesting about them is that they support a lot of very efficient inference and a lot of efficient algorithms. So we started out by looking at trees that could have an arbitrary number of children. So a given node that exists within the tree structure, however you decide to build it, could have many different children at one time. And so in order to do that, if we look in the code that I'm sharing with you under section 1 in CS-030 section 1 tree.java, you see that a description of the node has the data that the node is storing, because the trees are fundamentally for storing data. So you see the data that the node is storing, and each node stores like one chunk of data. And then you see all the children that are possible in line 15 that are children of any node. So this is recursive, so a node can have children, and its children can have children, and its children can have children, on for 1,000 generations. It's the UK blessing. A special case of the tree, though, is when you don't have an arbitrary number of children, but when you have just two children. And in two children, that's listed under section 2 in the code that I'm sharing, you can see that the node class, which starts down on line 40, still has the data stored in that particular node. Again, a binary tree is a special case of a tree structure, still stores data at each of its nodes, but instead of having an array of children, we only have two children, and we've changed their name. We don't call them child 1 and child 2, we're calling them left and right. Because it's a binary tree, there are only two ways you can go for children, and we choose to name them left and right. We can name them whatever we want, but that helps with the visualization a little bit. We then saw that we could use these kinds of binary trees in some specific cases. We could use them in Huffman encoding. We could use them in decision trees. There are a lot of different places where they are helpful as a data structure, and they're sort of you can create shapes of trees using the binary tree data structure that has all the same expressive power as a tree that has multiple children per node. So the fact that it's binary doesn't really change its expressive power. It actually kind of makes it more simple and in some ways kind of a pure data structure in that way. So what I want to do today is I want to look at binary search trees and talk about the way binary search trees are different than both trees and binary trees. The key word there is search. And the key thing that we're doing in order to make a binary tree into a binary search tree is we're adding an additional constraint. And that additional constraint is that there's going to be a relationship between the data that is stored in the node and the data that's stored in the children. And that relationship will be a greater than and less than relationship, or greater than or equal to. Depends how you structure your tree. So in this diagram, it's an abstract idea of how this is being accomplished. And so what we've got here is we've got a binary tree. It's a binary tree because it has two children. The square node represents a node, or the square red block represents a node, and the triangles represent an entire tree data structure, which could have one or more data nodes below it. But the part that I want to draw out here is that all of the data that's stored in nodes that proceed down the left side of the children, the left branch, are all going to contain data that is less than the value that's stored in D. And all of the nodes that are down the right path, the right child of D, all have to have data that's greater than D. And so just by focusing on D as one particular node in a tree, perhaps it has parents, perhaps it doesn't, but we can focus on it as if it's a root, because it's certainly a root of a subtree. We can focus on that D, and we can say that all of the data that is stored in this tree has been split into two groups. On the left side, following the left child, are all the elements in our tree that are less than D, and to the right are all the elements that are greater than D. So the descendants to the left have a smaller data value than the node at the top, and the descendants to the right have a larger data value. If D is exactly in the middle of the entire data set, then you're going to have the same number of nodes to the left and to the same number of nodes to the right. But a binary search tree doesn't require that. It just requires the property that everything to the left, whether that's one node or a million nodes, is less than D, and everything to the right stores data that's greater than D, whether that's 0 nodes or a million nodes. It doesn't matter. The property is less than and greater than on the two children. So if we want to structure a tree that contains, let's say, strings in this case, we can determine whether it's a binary search tree first by recognizing whether it's a tree or not. And so it fulfills the requirements of a tree, which is that there's a node with children and there's no loops in the structure that like kind of go back to the top again or something. We can see that it's a binary tree because every child has only one or two children, 0, 1, or 2 children. And we can additionally see that it's a search tree because at every single node, if we pick that node and look to the left and to the right, everything to the left of our root node of whatever subtree we're looking at has something that's alphabetically earlier. And everything to the right has something that's alphabetically higher. So let's start at the top and just examine this in the case of Juliet. So Juliet, to the right, Juliet starts with J. So to the right, we have Romeo and Tom. R and T both come after J, so that's good. As we look to the left, we have Adam, Eve, and Harry. A, E, and H all come before J. And so just by focusing on Juliet, the search property holds. But to make sure that this is a search tree, we have to make sure that it holds for every node. So let's go down the left side and let's examine Eve. Is it true with the subtree rooted at Eve also? Well, E starts with E. Everything to the left of Eve is Adam, and that starts with A, so the property holds at this subtree. And to the right is Harry. So H comes after E, A comes before E. There are no other children of Adam and Harry, and so the left side of the tree that's rooted in Juliet, every node maintains the search tree property. Let's go down the right side. So if we go down the right side of Juliet and we look at Romeo, treat Romeo as the root of a subtree, we can see that everything there's nothing to the left. Well, that's okay. If there's no data to be stored that comes alphabetically before R, then we don't need to put anything there. To the right side, we see that we have one node, the name Tom. T comes after R, and so the subtree rooted in the node Romeo is also a search tree. And Tom has no children, so that's great. So that's we can see that's pretty straightforward. Let me sort of point something out to you. If you were going to add a child to Romeo, and you were going to add someone down the left side, we know because of the property of search trees that the string that we stored as the left child of Romeo would have to be alphabetically before R. But because this subtree that's rooted in Romeo is actually a subtree, it's part of a greater tree, there's additional constraints by virtue of this whole thing wanting to maintain its search tree property of what the left child of Romeo can be. In particular, the left child of Romeo has to come alphabetically before Romeo, but it has to come alphabetically after Juliet. For example, we can't place Adam, let's pick another A name. We can't place Aaron, starting with an A, to the left of Romeo. Now, while that would be fine for the search tree rooted at Romeo, because A would be to the left of R and T would be to the right of R, so the subtree rooted in Romeo would maintain the search tree property. When we back up to Juliet, the right path, the right subtree of Juliet no longer maintains the search tree property because somewhere down as a child of Juliet is the hypothetical node Aaron, and Aaron comes alphabetically after J. And so if we put anything as a left child of Romeo that comes before Juliet, we've broken the search tree property. So that's a subtlety in the way that things are organized in a search tree that's important to note. All right, here's an example of a binary tree that's not a search tree. The left branch rooted at Juliet remains the same. Oh, no, it doesn't remain the same actually. We go down the left side and we see that to the left of Juliet is Adam, and that's fine, and Eve is fine, and Harry is fine. So A, E, and H all come before Juliet, so that's okay. But if we take the subtree rooted in Adam, the search tree property isn't maintained for all the children of Juliet.
So to the left of Adam is Eve, and E comes before A, so this is broken. H comes after Adam, that's okay, but this relationship between Adam and Eve, or the way in which Adam and Eve are placed in a tree, is breaking our search tree property. Also on the right side of Juliet, even though Tom and Romeo are both T and R, both come after J, and so it's great that they're on the right side of Juliet. As we traverse down the tree, the search tree property doesn't continue to be maintained at the subtree rooted in Tom. At the subtree rooted in Tom, we see that there is a branch to the right, and the letter R is on the right side. Well, alphabetically, R comes before T, and so that's a violation of the search tree property on the right side as well. So this is an example of a binary tree, but not a binary search tree. So that additional word search has meaning, and it conveys structure that's a relationship not just between the nodes and the links, but also between the data that's stored in these nodes as well. All right, so what this means is it means that when we implement this, when we create a binary search tree, I'm going to go back a second, we have to be able to tell where a different piece of data belongs in this tree. And that means that we can't just put any data that in these nodes anywhere. We have to put data in these nodes that we can compare so that we know whether it belongs to the left or the right. Much like the way in which we were sorting data earlier when we were talking about searching and sorting and had to implement our own compare to methods. So the same thing is true in a binary search tree. In a binary search tree, we have sort of the outer structure that we've seen in all of our tree data structures. When someone uses it as an API or as a library, we present them the binary search tree class. And internally, we keep track of a node. We can construct an empty binary search tree, or a user of our class can construct an empty binary search tree. And we don't actually allow them to create anything except an empty binary search tree because we want to make sure that this search property is maintained. So for someone who's using our binary search tree, all they get to do is declare that they want a tree with the constructor and then add data to the tree. And we're going to keep it in order as the implementer of the binary search tree so that it actually is a search tree. So to do that, we're also going to have a node class, and the node class is pretty straightforward. We've got our left and right node references, just like a binary tree. And we also have our data. That's good. That's kind of what we expect because we're storing data in our tree. But what's happened is instead of saying this data can be a reference to anything, previously this was object, now we're saying it has to be a reference to some class that implements comparable. This was the same restriction we placed on the classes that we wanted to sort using collections.sort. And the reason why we have to have data that's comparable, is because we have to be able to compare two nodes to know whether or not the data belongs on the left side or the right side of our tree. If we can't compare two classes, for example, you implement a class that is, you implement a color class, and it's not obvious how you would compare two colors in order to put them in order. And so if you don't implement some kind of a compare to method in your color class, it's not clear whether you actually have a binary search tree if you decide to create a tree full of colors. In order to have a search tree, you can only store data that's comparable that you can put into order. Otherwise, the idea of a search tree doesn't make sense because it implies an ordering. All right, so let's talk about the algorithm that we use when a user of our binary search tree wants to put some data into the tree. We don't allow them to put this data anywhere in the tree that they would like. We're going to insert it for them. And here's the way it's going to work. We're going to accept the data from the user as part of the add method that they're going to call. And then we're going to do a recursive execution of an algorithm to look through this tree to decide where this data belongs. We're going to start at the root. And if we encounter, this is a pseudocode, if we encounter a non-null node reference, meaning we are at a node that isn't dangling off the end of the tree, we're going to look to see what data is stored there. And if the data that we want to add to our tree is larger than the current node we're looking at, if the value that we want to insert is larger than, if the data at the node that we're currently looking at is larger than the value we want to insert, we're going to go down the smaller side of the tree and continue doing this insertion recursively on the left child. If the node's data value is smaller than the one we want to insert, we're going to continue recursively to try and insert this data down the right side, which is the larger half of the tree. If the node's data value is the same as the one we want to insert, we're going to just ignore it. We're going to ignore the request to insert the data, because what we're going to do for this version of the binary search tree is we're going to only have one copy of every kind of data in this tree. So if someone tries to put duplicate values in, we're not going to store it. The reason why we're doing that is because binary search trees are typically used to implement sets, and sets don't contain duplicate values. They only contain one copy of each data element. So that's just a detail. If at any point we encounter a null node reference, it means we've walked off the bottom of the tree, and we're going to take the data that we want to insert and we're going to tack it onto the bottom of the tree, just like we might have previously tacked data onto the end of a linked list. But this process of algorithmically going left and right is going to show us where in the tree the data should be placed so as to maintain this search tree property, the less than greater than search tree property. Here's what it might look like. We first create a new binary search tree using the constructor. We store a reference to it in the local variable tree, which is of type binary search tree. And then we're going to go through the process of adding 4 strings to this tree. Now, a string implements comparable. We don't have to do any work because Java, with its implementation of string, implements a comparable function for us. So that comes with the class. That's great. It's typically alphabetical, and that's great because we want to be able to sort things alphabetically. We're first going to add Juliet. And since our tree has no data at the root, Juliet becomes our root node. Next, we're going to add Tom. As users of the binary search tree, all we get to do is say, please add Tom. But internally, within the implementation of tree, what's going to happen is the code is going to start at the root and examine Juliet. It's going to see that Tom is greater than Juliet using the comparable function, the compare-to function. And so we're going to proceed down the right child of Juliet. At the point at which we've just added Juliet, there's no one to the right, and there's no one on the right child tree of Juliet. And so we're going to add Tom immediately as the right child of Juliet, maintaining our binary tree, maintaining a tree, a binary tree, and a binary search tree with just Juliet and Tom. Now we want to add Diana. So again, our user adds Diana, but on the implementation side, we start at the root, we examine Juliet, we recognize that Diana is less than Juliet, so we recursively attempt to add Diana to the left-hand side of the tree. The left-hand side of the tree is null, and so we create a new node to hold Diana, and we link it in as the left child of Juliet. Now having a tree with 3 nodes, Juliet, Tom, and Diana. Our user now asks to add a 4th data element to our tree, Harry. Internally, we do the same process. We take Harry, we examine Juliet, and we say, oh, Harry is less than Juliet. H comes before J. So we proceed down the left side, and now we do a recursive call, and we say, well, I would like to add Harry to the node rooted in Diana. Well, Harry comes after Diana alphabetically, so we're going to make a right node off of Diana and add Harry here. And so internally, we're maintaining this binary search tree structure. Externally, the user of our class is just adding data and isn't aware necessarily, unless they're keeping track of it on their own, of how the data is being stored within this tree. So an important property of binary search trees to recognize here is that the shape of the tree and where the data is stored in the tree depends on the order in which data is added to the tree. Just to see that in a very straightforward proof, if our tree is empty, whichever string we add first is going to end up being the root of our tree. So in this case, it started with Juliet. But if we had chosen a different one of those strings, our tree would have been rooted in a different string, and the resulting shape of our binary search tree would be different. So that brings up another observation. You can have data in a binary search tree, and the shape of that tree is not unique. You could have multiple binary search trees with 4 nodes in it, each holding this data, and there could be multiple different shapes of that tree, depending on the order in which you added the nodes. You could have any one of these nodes be the root, you could have any one of these nodes be the second element that's added, third element, and fourth element. And each one of those cases is going to give you a variant of the tree. I heard some typing. Let me check on questions. Uh, Josh asks, would someone add the most accessed elements of a set to the binary search tree first to gain quicker access, or does it not make that much of a difference? Okay, that's a really great question because it means that you're thinking about the efficiency of this search algorithm and you're trying to understand where the efficiency comes from. Um, Usually, when you work with sets, you don't know beforehand which elements are going to be accessed most frequently. And so you don't really necessarily know how that's all going to play out. Or you might not have control over the order in which elements are added to a binary search tree. For example, if you're accepting input from a user and you're taking that input from the user and you're adding it to your search tree, you add it in the order in which the user gives it to you. And you don't have flexibility over how to add it to the search tree. What I would say is that later in chapter 17, there is a data structure called red-black trees. And a red-black tree is an extension of a binary tree. And what a red-black tree does is it attempts to make the tree access, the tree search process, efficient regardless of the order in which people add the data. So red-black tree is something we haven't touched on yet, but it is an extension of the binary search tree, and it's really worth looking at in some depth. I'm not sure we're going to be able to do it justice, though, just given that we have one more lecture left. But the real answer to your question, Josh, is a variant of the binary search tree called a red-black tree. And the red-black tree is how Java implements tree sets. And so that's the actual algorithm that Java uses in order to keep a tree and the goal here is to keep the tree balanced rather than having common elements at the top. What you really want is you want your tree to have an equal number of elements on the left and right, regardless of the order in which you add them. But that's a great question because you're really getting to the heart of what we care about when we work with these data structures. Okay, so we have our 4-element tree, and now we add one more element as an example. Let's add Romeo to this tree. We recursively evaluate what we've got here. We start with Juliet. R comes after J, so we proceed down the right path. Look at Tom. R comes before T, so we proceed down the left path of Tom. There's nothing there, and so we add a new node for Romeo. Okay, so what does that look like in code? Our add method for the binary search tree. Okay, so notice that we've got, this is in the tree class. So this is the method that people are calling, like right here when they do tree.addRomeo, this is the method that they end up calling. It's the add method in tree. All right, so what do we see here? It's a public method. It's not returning anything because it's just changing the data structure. It's taking some kind of data that the user wants to store, Romeo in this case, and it's got to implement the comparable interface, meaning it has to be comparable to something of its own type so that we can figure out if it's greater than or less than. So what are we going to do to add something to our binary search tree? We're going to start by creating a new node that's going to hold this data. We don't know where we're going to put it quite yet, but we do know that at some point we're going to need a new node and we're going to need to place it in our tree. So we're going to get that ready. We're going to create a new node. We're going to create a home for this data, a reference to an empty node, and then we're going to set the instance variables of this node to what we care about. So we're going to make data be a reference to the object that the user passed in. So data will point to Romeo. We will set the left branch of the node to null because there are no children yet. The right node to null, so just kind of getting our node ready so that we can move it around. And now what we're going to do is we're going to consider recursively how we're going to add it to our tree. So we're going to start and we're going to check to see if there's any data present in our tree to start with. And the way we do that is we ask if root is null. So if the root of our tree is null, there's no node there's no starting point in our tree. We must have just come off of running the constructor. And so what we're going to do is we're going to place the new node that we just created. We're going to have our root reference point to the same data that new node points to. And so now root has a reference. It's no longer null. And our binary search tree consists of just one element and the data in that one node, and the data in that node is the object data. And we return. Notice that we return from the add method, no recursive call. In the case where root is not null, this is the situation where we have to traverse down the tree. We're going to kick off our recursive process by using a helper method called add node, which is implemented in our node class, not in our tree class. And what we're going to pass to add node is this nice little packaged node that we've already created that has the data that we want to add. Notice that the user of this class has never interacted with the nodes at all. What they've done is they've passed in the data that they've cared about. We've internally created a node, and we've internally passed that new node to a method of the root node, but our user has never interacted with root. Our user has never interacted with the node class. That's abstracted away. It's an implementation detail. Our user doesn't need to know how we're implementing our binary search tree. All the contract is with the user is that we are maintaining a binary search tree for them. Okay, so kicking off our add node recursive call. Now we go into the interior class, the inner class node. We look at its add node method. It takes in the new node that we want to add. So this is kind of like the way in which the trees add method is structured, except that this is structured for internal use only. It's like the section on the forms that the registrar gives you over to the right that's ominous and says for internal office use only. That's what this method is like. It's for internal class use only. We are in some node. So remember, we are a node. So we are a location in the tree. And now someone has asked us to add this new node, given our identity as a member of the tree already. So given that we are a member of the tree, we now need to do the recursive work of placing this new node. So we're going to run our compare to method. We're going to look at the node that is coming in. We're going to get the data from it, and we're going to call the compare to method. Well, now this would be a problem if this data was of type object, because something that is of type object doesn't necessarily have a compare to method. And so we might try and call a compare to method and have our code crash if our data didn't have a compare to method. But because we said that our data had to be had to implement the interface comparable, looks like we're using the type comparable, we know that what that means is that it has to have a compare to method. And in fact, all we know about it is that it has a compare to method. So we're going to look at the data, the reference coming in. We're going to look at the data that's stored there. We're going to call the method that we know is implemented because of the way we typed it. And we're going to pass it the data that we're storing as an active node in the tree. And the result that comes back is going to be an answer of which branch of the tree we should follow. We know if comp is 0, we know these two data elements are equal. And so if it's 0, we're actually just going to return. So notice that our cases here are if comp is less than 0 and if comp is greater than 0. If comp equals 0, then we're just going to return, not actually adding the node at all because that data is already present in our tree. And since we're going to sort of treat this as a set data structure, we don't need to store an element twice. Okay, so if comp is less than 0, that means that data is the new data that we want to add is less than the data that's currently present at this node. And so we'll check to see if there's somewhere to send it. If our left child is null, that means we have no branches off the left side, and that's easy enough. Then we're just going to graft in this new node. And we'll say that our current node's left reference was null and will now point to the same thing that new node points to. And bang, we've grafted in this new node to our tree. We finish that and we immediately return. If there is a left child on the current node, rather than trying to graft it in, we're just going to pass the buck. We're going to send the responsibility for adding this new node down the left-hand side of the tree. And we will recursively pass off the responsibility to whichever node is down the left-hand branch of the node that we're currently at. Moving down the tree is getting smaller. We know that we have an ending condition of some point when the left node is null. So we have a pretty clean recursive solution down the left path. Either left is null and we stop recursing, or left is not null and we pass the buck and ask our left side to do our adding for us. All right, well, what if comp is not less than 0? What if the new data that we want to add in is greater than the data that we're currently storing? Well, we do the same process, but down the right side. We say if our right side is equal to null, that means there's no children down our right side, and we're just going to make this new node be our right child. And so our right reference is going to point to the same thing that our new node reference points to. However, if we do have right children, again, we're going to pass the buck. We're going to kick the can down the road. We're going to leave it for the next generation. We're going to use the right reference. It's a node class, so we know it has the add node method. We're going to pass it the data that we want to add, and then recursively, this whole method will get run again, but not at the current node, but at the child to the right, down the right-hand path of us. Again, our problem is getting smaller because we're recursing down a smaller subtree, and there's an ending condition down our right-hand path because at some point we're going to run out of tree, and at that point we add our node. And bang, we've returned, and we get this sort of sequence of behavior that we saw here with our Juliet, Diana, Harry, Tom, Romeo tree. What about removing a node from our tree? How do we pull that off? Well, the first thing to do when we want to remove something from our tree is we have to find our node. And finding the node is very similar to the way in which we added a node. All right, and there are a couple cases that we have to consider here. And this kind of case processing, thinking about the different cases that a tree has to work with in order to make the algorithm work, is really common for tree algorithms. So let's take a look at this. Here's one case. If we have the case where the node that we want to remove has no children, well, that's a pretty easy case, because what that means is, for example, in this diagram figure 13, the node to remove is on the bottom right, and all we do is we say the parent's right child used to point to this node we want to remove, so now instead we're just going to set our right child of parent to null. Because our node that we want to remove has no children, we lose no data, and it's removed from our overall tree. Parent will now have a left child and no right child. Easy case. Case number 2 gets a little trickier. This is the case when our node to be removed has one child. Okay, well, turns out that this isn't too bad. We can maintain our search tree property pretty straightforward with this solution. What we have to be careful of is that we don't set the right child of parent to be equal to null, because if we do that, we're not just going to delete the node that we want to remove, but also all of its children, and we know it has one child. So instead, what we want to do is we want to make the right-hand path of parent point to the child of node, whether it's left or right, because it only has one child, and then we will have lost the node reference in our tree, because there will be no path to node anymore, because we'll go from root to parent to the rerouted link to the child, and the parent will be collected by or the node to be removed will be collected by the garbage collector, because nothing points to it anymore. The hardest case is when a node has two children. The node that we want to remove has two children. Conceptually, what you want to do is straightforward, but the code to do it takes a little bit of thinking. So in this case, we have a tree, and the node that we want to remove is the immediate right child of the root. Now notice this is tricky because the node that we want to remove has children down the left branch and down the right branch. And so we can't easily just place the left child or the right child as the child of our parent right here. We can't just make this point to left or right because we've got two branches and only one reference that we can move in. So we have to do this recursive procedure. And the recursive procedure is to start at the node that we want to remove, and we want to find the smallest node of the right subtree. We want to find the node that has the smallest data value on the right-hand side. And what we're going to do is when we find it, we're going to move that data up to replace the node that we want to remove, and then recursively do the removal action for this second node that we want to remove. And in this case, the diagram shows it has one child, and so we can just reroute the link around it. What this does is it reorders the positions of the nodes in the tree, but it maintains the search tree property because we have replaced this element with the smallest element that's still greater than this node. And the smallest element that's greater than this node is greater than all the elements on the left-hand side. Really elegant kind of way of doing this. This process is a little recursive heavy, so we need to watch that. We'll take a look at the code in a second. What I want to point out to you here is getting a little bit to Josh's question about the efficiency of these operations. How efficient is it to add locate, or remove an element? Well, basically, we say that in a balanced search tree, the time it takes to do these things is order log n. Now, if you recall from some of the formulas that I showed you in the last lecture, log n in a binary tree is the height of the tree. And so when we say something is order log n and we're talking about a tree, we're saying it takes the amount of time that's equivalent to the height of your tree. All right, so let's look at what that means. Let's just focus on the left-hand column for a second. How long does it take to find an element in a tree? Well, think about what that entails. You have to look at the root and decide whether to continue your search on the left-hand side or the right-hand side. You do the comparable operator to do that. But what's interesting is that when you decide to go left or right, you don't have to look at anything at all on the other half of the tree. You only have to proceed down the half of the tree that contains the data that you're looking for. Much like when we played that number guessing game in class, and I asked, I forget who it was, to pick a number between 1 and 100, and to find it, I picked the number 50 and asked you whether it was less than or greater than. And that cut my entire search space in half. That's where we get the power of this tree data structure, is that we can cut our search in half every time we ask one question of our data. So finding an element, on average, takes the height of the tree, because although we do have to proceed from the top to the bottom in general in order to find an element, we don't have to search all of the tree. We only have to find one path from the top to the bottom. Now, it's important to recognize that that's a huge savings. So let's say that we have a tree that has 65,535 elements in it. That happens to be 2 to the 16th power minus 1. And so that means that we have a tree of height 16. So instead of having to search 65,000 elements, we only have to search 16 elements. That's the difference between order log n and order n. It's a huge savings in time. Likewise, in order to add an element, the process is very similar. It's maybe even more clear. Because in order to know where to add an element in our tree, we have to look at the root and decide whether it belongs on the left or right based on its value. And then as we proceed down the left or right path of the tree, finding where our element belongs, we only at each junction in the tree need to make a decision about going left or right one direction. And eventually, we've walked down a path from the root to a leaf that is the height of the tree, and then we add our element to the bottom. Removing an element turns out to be the same for much the same reason as well. The analysis is a little bit more complicated because of the recursive property, but it's basically the same. Now, what I want to point out to you, though, is the difference between these two columns, a balanced binary search tree and an unbalanced binary search tree. And the reason why I want to draw these out is because the fact that your tree is balanced or not makes a big difference in the running time. This, again, is kind of getting back to the way I answered Josh's question. The key insight here is to recognize that an unbalanced binary search tree is the same as a linked list. Imagine a binary search tree where you only have data that goes down the right-hand branch of every node. You go root to right, to right, to right, to right, to right. There's no splitting. All of your data proceeds just down one line of your tree. It's effectively the exact same structure as a linked list. And so then we look and we say, well, how long does it take to find an element in an unbalanced binary search tree? Well, in an unbalanced binary search tree, the height of your tree is the same as the number of elements in your tree. So if you have 65,000 elements in your tree and they're all on the right-hand side, go down the right-hand side of your tree, then the amount of time it takes to find an element on average is order n time. So on average, you have to search half your linked list in order to find things. Sometimes you get lucky, it's at the beginning. Sometimes you don't get lucky, it's at the end. But we throw away that 1/2 constant and it's order n. Same thing with adding an element, it's order n. Same thing with removing an element, it's order n, because we have to search the entire right-hand child lengths in order to find the tree. And this is exactly the same running time as a linked list because it is effectively a linked list. And so the difference here is on the left-hand side, if you have a balanced, bushy binary tree, you get a huge time savings. But if you have an unbalanced binary search tree, you don't get that time savings. It's very important that you have a balanced binary search tree to get efficiency. But you saw that we don't get to control that. When we add the data, Romeo, Juliet, Tom, the shape of our tree is dictated by the order in which data is added to our tree, which we may not know in advance. And so what we need is we need additional mechanisms, we need additional complexity in our algorithm that will cause our binary search tree to become a balanced binary search tree. And we're willing to accept the additional complexity of the algorithm in order to get the additional efficiency of working with a balanced binary search tree instead of an unbalanced binary search tree. And then going back full circle to the answer to Josh's question, a balanced binary search tree is implemented as a red-black tree. What we've looked at so far is an unbalanced binary search tree. And if you're lucky, you get order log n performance, but you can't guarantee it the way you can in a red-black tree. All right, before we get there though, I want to, something that is very important both for the exam and for your education is to talk about tree traversal. We have 5 minutes to start this concept, and I'm going to spend the next lecture probably talking about tree traversal and then just introducing you to the idea of red-black trees, but not going in great depth. Red-black trees take a little bit of time to get your head around. We don't have that time. So let's a binary search tree implementation is in the code that I shared today. If you'd like to look at it in more detail to see how it's implemented, we can run it real quick just to demonstrate it. So on screen here, I'm placing Eclipse, and we have the code is in section 3. It's called Tree Tester. Some of you are still connecting. I'm not sure what's up with that today, but we can try again after class. What our tester does is it simply acts as a user of our class. It creates a tree T. It adds some data to the tree, which are going to be strings, capital letters. It adds them in this kind of arbitrary order, and then it removes them in kind of an arbitrary order, A, B, F, D, and then it prints out the tree. And it's this printing out of the tree that I want to talk about a little bit, because what we don't have here is we don't have a convenient visualization. We don't have a convenient way within Eclipse of showing the trees with like little red squares like I've been doing in class. And so you can do this manually in order to see that it's working okay, but we need to talk a little bit more about tree traversals to understand what's happening. So I'm running it, I think. In the console, you see the output, and C, E, G, H, I, J is what we expected. Why we expected that remains to be seen. All right, so let me get us started on tree traversal in the last moments that we have left. If we want to print a binary search tree in sorted order, here's how we can do that. Now remember, it's a binary search tree, so the data present in it maintains an ordered relationship. If we want to print all the data that's in our binary search tree in sorted order, the way we can do that is with a recursive pseudocode algorithm that does this. First, print the left subtree, all of the data that comes before the node we're currently at. Then print the data at the node that we're currently at. Then print all the data in the right subtree. This will walk through our tree, printing everything in order. This is also called in-order traversal. In-order traversal is one of 3 different ways that we recursively traverse trees that you need to be familiar with and understand and be able to duplicate. Here's a recursive helper method for how we can go about doing that tree printing using this in-order method. All right, so here's what we've got. We've got a method within our node class that's going to accept some parent node. Oh, I'm sorry, this is... where is this? This is going to be, yeah, this is in our node class, because in our tree class, this is where we kick it off. We say we're going to print from our tree. Our tree is then going to call the node class and print the root. So starting at the root. All right, so printing is static, so it's not using any of the variables. It takes root as a parameter, and it checks to see, okay, if the parent node that we're starting at, the one that's passing the parameter, is null, then there's nothing to print. We're at the ending condition of the recursion, and we go return. We do nothing. However, if the parent is not null, then we recursively print the left-hand side. Notice this isn't system out. This isn't system out.print. This is our own print method. So we're going to print the parent.left. Now it's possible parent.left is a null reference, but that's okay because when we recursively come in here and we pass node and node is null, we're going to check that right here and quit. So that recursive call in null is fine. After we print our left-hand child, we're going to print the data that's currently present in our node, followed by a space, and then we will ask the right-hand side of the tree to print itself. And then we'll recursively drill down on the right-hand side. And this will, in a recursive method, go through our entire tree using what we call an in-order traversal. And if we are doing this on a binary search tree, the data in our tree will be sorted. We don't have to have a binary search tree in order to do this printout, in order to do an in-order traversal. An in-order traversal doesn't depend on having a binary search tree. It only depends on having a binary tree. But if we do an in-order traversal on a binary search tree, it's going to print out the data in a sorted order. We spent an entire chapter talking about how long it took to search and sort data. And I'm telling you right now, without any explanation, that if you just do a recursive algorithm on a binary search tree, you get the sorted data apparently for free. Why? How did I just pull that off? I just argued that I can print out all the data in your search tree in order without ever calling sort. And that's the mystery that we're going to explore in our last class together on Wednesday. Any questions? Also, I really like computer science. All right, let me switch to in-game audio. Okay, broadcasting just in class, not on YouTube. YouTube's still broadcasting, but the audio is not. We're in class audio. Questions or comments? Wait, our computer science professor likes computer science? I know, right? Like you'd think that would be obvious, but like it's not clear that like necessarily people are doing jobs that really give them life, right? Uh, that give them joy, etc. Sometimes people do jobs because they need to make the money or whatever. I'm fortunate that I both get to do something that feeds my family and that I really enjoy. Yes, I am double broadcasting. It's a feature, not a bug.
or broadcasting YouTube. All right, I'm broadcasting YouTube again, and we are shutting down for the day. This has been April 26th, CS-030. We're looking at trees. One more class. It's a good day. Shutting down broadcast. Thank you for your attention today. All right. See you later, everyone.